Next speaker is William Cornell from Denison University. And the title of his talk is Optimizing Computational Analysis Through Massively Parallel GPU Computing.
My name is William Cornell, and I also work with Dr. Tevra at Denison University in the Biophysics Lab. And this summer I was looking at optimizing our computational analysis using GPU computing. So just a little outline, just talk about a little more about what the Biophysics Lab does at Denison, then just an overview of what parallel computing really is, give you a brief overview of the molecular dynamics that we do, and then how you can speed it up with a programming environment called CUDA. So at Denison we study molecular motor, here's the same cartoon you've seen. That's myosin 6. And Amanda just talked about normal mode analysis, which is a pretty quick way of computationally doing analysis, but most of what we really do that's computationally intensive is molecular dynamics. Huge simulations that take, hours and hours and hours to run. And we run those on machines with really, really expensive graphics cards. We used to have to rent time on an off-site CPU cluster or something to get our simulations to run. But these days with graphics cards, you can actually run simulations a lot faster. So this is a picture of the machine that I built this summer for the lab. And just a little about parallel computing. We used to, and still a little bit these days, speed up computers by just speeding them up, increasing the frequency with which they do calculations. But the higher the frequency, the more power a CPU uses, and the more power you use, the more heat you use, to the point where you need to use all these fancy tubes and liquid and radiators to keep it cool. It's almost as complicated as a car. And so they started adding, they started out with dual core CPUs, right? They basically put, if you're familiar with it, 2 CPUs on the same chip pretty much. And this all works around the idea of threads, where you have basically many hands make light work. You've got multiple workers, multiple CPUs working on subsets of some larger problem, and each one solves its sub-problem, and then at the end they sort of combine their results into a finished product. So in the sciences, GPU computing started off pretty rocky. When it was discovered, you could sort of trick a graphics card, which is used to doing pixel shading calculations, to figure out how these 2 million pixels, what color each one of them should be. You could actually just trick them into doing math on whatever data you want. But that involved early on learning a shading language, and there weren't debugging tools. And there was also no guarantee of what kind of precision your graphics card was capable of. So it's not, printing this image is not scientific research, so they don't really need the same precision. And then NVIDIA developed the CUDA programming environment for their brand graphics cards that allows you to program with basic C syntax that any programmer would know, with some new keywords and built-in functions. And they also guaranteed single precision floating point arithmetic would be compliant with the standards. And actually these days it's also double precision capable. So the molecular dynamics that we do produce a lot of data. And we've moved these to GPUs, and they run a lot faster, but they still produce a lot of data. And currently we analyze this data with CPU programs. And it takes actually longer than the simulations we have to run, because they output, we've got this kind of chart of what it outputs. It's a total of about 25 gigabytes of data, and it's pretty much just a movie of these proteins moving, snapshots or frames of the XYZ position of the whole protein in space as a function of time. And these movies are not really all that useful on their own. We have to get some sort of useful data out of them. So here's what, if you run it into a visualization program with VMD, protein wiggling, this is myosin 5. And so one of the big things that we do is called covariance. where it's an n by n matrix, where n is the number of amino acids. And it's a relationship between the different amino acids in the protein, and it's how they move relative to each other. So orange is that they're moving apart from each other, blue is that they're moving towards each other, and white is that they move with each other, like in the same direction. And so you can see here it's symmetric about the diagonal. It should be, the relationship between 200 and 400 should be the same as the relationship between 400 and 200. And you can see here the big nasty equation that you have to do. It's actually just a cosine. It's pretty simple. It's their relative change vectors. The change here that we're measuring is relative to the reference structure in the simulation. And so doing it on a CPU, it's a three-dimensional loop. If you've done your programming, here's a little C snippet. So you loop over every single frame of the movie, and you loop over n twice. And in the body of this loop, you calculate the covariance of a single index for one frame. You add it to a running sum, and then at the end, you divide each point in the matrix by the number of times that you went through that loop. The complexity of it, it scales as n squared times m, where n is the number of amino acids you have and m is the number of frames. So it takes quite a while as you get large amounts of data. 25 gigabytes of data takes at least 10 hours. So you're looking at, you start your analysis code after having run your simulation for a day, you start your analysis code and you have to come back the next day to get any useful data. So I first looked at parallelizing it in one dimension, where you have the same loop structure, but rather than looping over n twice, you have each thread, you allocate n threads, you have each thread handle a whole row of the matrix. So then you can cut it down by a factor of n, so it's the complexity is just as n rather than n squared, and no race conditions. This is kind of important with parallel computing. If you have multiple threads working on the same data locations in memory, you're not guaranteed which thread is going to finish working first. Some might be a little faster than others. So you can't guarantee that one is finished writing to a memory location before another tries to read it or write to it itself. So you get data corruption with that. And here, because each thread is handling a different row, they're working with different data, you don't run into that. And here's just a sort of diagram of what a multi-core processor looks like, where you have multiple cores, each with their own set of memory, and the shared memory, which is where you run the race conditions. And then this data is a two-dimensional array, and CUDA allows you to allocate a two-dimensional array of threads. So you can actually have each thread, you can get rid of that other factor of n by having each thread handle a single index of the matrix and go through every frame. And so you reduce the complexity to order n. And again, you have no race conditions because everything's working on a single index of the matrix. And we use two different, really three different, but I tested two different graphics cards that we have in the lab. The GTX 690, which is a dual GPU graphics card. Here I was only testing it with a single GPU. And the GTX Titan Black, which just came out this past year, against the i7-3930K, which is a 6-core CPU from Intel on single thread performance. And so the previous CPU version takes about 11.5 seconds per 1,000 frames, where you see about time in seconds versus 1,000 frames. So it takes about 8 hours optimistically. The 690 takes about 0.228 seconds per 1,000 frames. It's about 51 times faster. And the new Titan cards are about 96 times faster than the CPU code. But I really want to get just over the 100 mark. I want to get those triple digits. So I looked into constant memory. These graphics cards have 64 kilobytes of memory that you sort of trade off faster memory by saying that this memory you're not going to change. You're going to populate it with some data, and that is data that you only ever read and never change. And it's faster to read. It's cached, so consecutive reads of the same memory index don't don't incur any more memory traffic, and you can actually reduce the number of memory calls by 16 by having adjacent threads share their calls. So with this 15% increase in performance that I got from the constant memory, it reduced the time from 5 minutes to 4.4, and it's now just over that 100 mark, 110 times faster. So rather than waiting a day and having your code run overnight, you can now do it in under 5 minutes. And further optimization, I'd like to do 3D parallelization, which you have problems with race conditions. We can get newer hardware every year. There are a couple other measurements than covariance that we'd like to do. And multi-GPU programming where you use multiple cards and some other CUDA parameters. Any questions?
Okay, questions for William?
I was wondering when you use cache memory, could you use double precision for that?
Our simulations are stochastic and averaged, and double precision doesn't help us because the averages are only really helpful out to about 6 decimal places. So double precision, our simulations are all single precision.
You expect a sort of speed up just from going from one core to many cores, right? So how many more cores are you using?
The Titan cards have about 3,000 cores. I don't remember exactly the number, but it's in terms of speed, it's 5.1 teraflops of single precision.
And that's the so then you could sort of naively, old-fashioned programming expect a 3,000 times speed up. Is it the reductions that take place?
As you can imagine, each core is not quite as complicated and then as fast as the cores of the CPU. If you look at just frequency alone, the 3930K that I benchmarked against is at about 3.4 gigahertz, I believe, and the Titan card runs, depending on how hot it is, at around 1,000 megahertz. So it's almost 4 times slower just in pure frequency, but there are some other hidden issues of you have to copy memory from the host to the device. And, but in terms of just gigaflops relative, it's about 110-fold is the expected increase.
I think we have 2 more questions. I think Sean.
That was exactly my question.
Oh.
How much GPU programming experience did you have before the start of the summer?
None at all. I read a book and tried to figure it out.
Okay, let's thank the speaker again.